The eruption created a rift nearly 2 miles long across the eastern edge of the island, throwing up a torrent of boiling lava. Tonight, the eruption is gaining in intensity and the rift is still developing, northwards now beneath the sea.
This is the island of Jaime, which erupted in January 1973, 100 kilometers south of Iceland. The island situated on the mid-Atlantic ridge. The magma that wells up along oceanic rifts is erupted as basalt lava at around 1,000 degrees centigrade. A great number of fine particles of lava were ejected by escaping gases. The local fishing village, Vestmannaeyjar, was buried under several meters of volcanic ash. Basalts are by far the most common type of lava, and most of them are erupted in oceanic regions. This is Hawaii, the best studied of all volcanic areas. Many basaltic volcanoes have craters and calderas. This crater, in one of the Hawaiian volcanoes, is filled with molten lava. Because these magmas are hot and not very viscous, they flow down the volcano quite fast. The lava flows in channels bordered by banks of older solidified lava. The banks grow higher as more and more cooling lava is added to them, until eventually a solid crust grows right over the top of the channel, forming a tube which supplies new lava to the front of the flow. Inside and beneath the volcano, these magmas contain a high proportion of dissolved gas. This is released at the surface and escapes from cracks and holes above the lava tubes. The basaltic lavas, which are so common in Hawaii, form distinctive surface features. These are called pahoehoe lavas, a local Hawaiian name. Lobes of lava are rolled over each other as the flow advances. The surface also becomes wrinkled as the congealing skin is crumpled up on the cooling lava. This wrinkled surface is well preserved, frozen into the surface of the lava flow. But not all basalts are erupted without violent explosions. Surtsey grew out of the sea in 1963 on top of the mid-Atlantic ridge. It's built of loose, dark volcanic fragments. In the early stages, the sea had access to the erupting vents, and this produced the steam explosions which characterize shallow submarine eruptions. There are many basaltic volcanoes on the continents as well. This is Mount Etna in Sicily, the largest active volcano in Europe. Even though Etna is sitting on top of 30 kilometers of continental crust, these magmas are generated in the mantle and have risen from deep beneath the Earth's crust. Lava is carried to the flow front in tubes and channels. Many of the lavas are erupted near the summit, and they flow up to 20 kilometers down the side of the volcano. The channels curve and change direction as the flow encounters obstacles. This one has been diverted round a cinder cone. These cinder cones mark the sites of eruptions which occurred well away from the summit. They're small volcanoes, built of bombs and ashes thrown out of the volcanic vent. Most of the lavas are basalts, but very few of them form Pahoehoe structures. This flow, like most on Etna, is covered in rubbly scoriaceous blocks, which were broken up by the movement of viscous molten lava beneath. These are called A'a lavas, another Hawaiian name. The structure of the individual lava flows is pretty much the same all over Etna. They vary a bit in thickness. This one's just about average. But virtually all of them have got this rubbly base, a massive interior with vesicles, gas bubbles formed as the gases escape from the solidifying magma, and the rubbly top to each of the flows. The rubbly blocks fall down the front of the advancing flow where they're overridden. These flows are more viscous than the Pahoehoe lava seen in Hawaii, perhaps because they're erupted at lower temperatures and have slightly different compositions. The lavas erupted in Hawaii, Iceland and Etna are mostly basalts with silica contents of between 45 and 52%. Continental volcanoes sometimes erupt magmas which have much more silica and which are much more viscous. These are called andesites and rhyolites. In May 1980, the eruption of an andesitic volcano was well documented. Mount St. Helens in the western United States gave one of the most violent eruptions ever seen. The top 400 meters of the volcano were blown off, erupting millions of tons of pumice, gas and ash. After that, a new lava dome, just 200 meters in diameter, was pushed up to the top of the vent, waiting to be exploded off again. Here the gas is trapped in the viscous, silica-rich magma inside the volcano. If the pressure builds up, the gas may be released explosively to produce another violent eruption. The products of these eruptions are spread across thousands of square kilometers of the surrounding countryside. Sometimes, large-scale subsidence and explosion expose the internal structure of the volcanic pile. This is a solidified pipe, which once fed magma to the surface. And this is a dike, a wall of solidified magma which may have once fed a fissure eruption. It's fairly easy to study the superstructure of active volcanoes by direct observation. You can also find out a certain amount of what goes on inside them by indirect geophysical and geochemical techniques. But it's possible to find out more by looking at the eroded remnants of extinct volcanoes. During the early stages of the opening of the North Atlantic 60 million years ago, Western Scotland and Northern Ireland were areas of intense volcanic activity. Remnants of the vast plateau lavas erupted during that period are scattered throughout the Inner Hebrides and along the west coast of Scotland. A well-known outcrop of these lavas forms the cliffs around Fingal's Cave on the Isle of Staffa. The magnificent columnar jointing in the central portion of these cliffs is characteristic of basaltic lavas which have cooled slowly. Most of these plateau lavas have been eroded away, and a number of intrusive centers, which are the roots beneath the original volcanoes, have been exposed on the islands of Skye, Rum and Mull. These ancient centers lie roughly on a north-south line along the western coast of Scotland. They're all more or less circular in shape. One of the most impressive centers is preserved on the mainland, on the Ardnamurchan Peninsula, the most westerly part of the British mainland. This remote area on the west coast of Scotland was once a vast pocket of magma, and these outcrops were molten rock at a temperature of around 1,000 degrees centigrade. Even though we're well below the ancient volcanoes here, there are still some rocks left which contain very clear evidence of volcanic activity. The rocks that form this small cliff are called vent agglomerates. The rock is composed of blocks of a variety of different rock types, and these are surrounded and bound together by a dark, fine-grained matrix.
Well, how do such vent agglomerates form? Obviously, we need a supply of volcanic gas, which would be charged with particles of basaltic ash and perhaps tiny fragments of the older rocks. And as that rose through the volcano, it would tear off fragments of the older igneous rocks, the intrusive and volcanic rocks. These would be carried up in the gas, being rounded and broken and transported up towards the surface and possibly erupted from the Ardnamurchan volcano. Well, if we look at the surface, we can see that it's absolutely jam-packed with a different range of fragments, large and small fragments. You can see that some are very dark in colour. They're obviously intermediate or basic igneous rocks. And some are much lighter in colour. They're acid rocks, such as rhyolites. In fact, I've got a piece of rhyolite here that we've picked up and obviously represents a block from within the agglomerate. And the most striking feature are these very nice lines that run across it. They are in fact flow lines, and they must represent the flow of fairly viscous, pasty acid magma out of the volcano. There are also some different rocks which we can see in this block. A piece of rock here is fairly pink in colour. It contains pink feldspar and tiny amounts of quartz, and so it must represent a coarser rock such as a granite. The fragment here is speckled and composed of equal amounts of ferromagnesian minerals such as pyroxene or amphibole and plagioclase, so it must represent a diorite or gabbro. But besides the igneous rocks, we can find some rocks that are composed entirely of quartz. This fragment here is sandy quartz grains, so it must represent an older sandstone that's got caught up in the agglomerate.
This is Mingery Castle on the south side of the peninsula. The builders of this ancient castle made good use of the local stone, and it's located on a splendid piece of geology. A castle sitting on a sill, an igneous intrusion in sedimentary rocks placed parallel to the nearly horizontal bedding planes. Here's the contact, and below it are the quite nicely bedded sediments, the siltstones and shales that have been baked by the heat of the intrusion. The sill is actually in two layers. The upper grey layer has got some columnar jointing in it, and this dark lower layer is quite different. It's basaltic in composition. These specimens are from each of the two layers. The grey rock is medium grained, and it's got some feldspar phenocrysts. And the dark layer's fine grained, and it hasn't got any phenocrysts. But right at the very base of the sill, immediately above the sediments, the dark layer's even finer grained. And that's because the hot magma was rapidly chilled as it came in contact with the cold sediments. The magma moved along the bedding planes and wedged the strata apart as it went. But it didn't always stay exactly parallel to the bedding planes, because in some places the contact cuts across the bedding. This sill is a bit unusual in having two layers, but like all sills, it's a concordant intrusion. But lots of shallow level intrusions are discordant. They cut across the bedding. This is a dike, a vertical sheet of basaltic igneous rock, nearly 5 meters across. It's cut right up through the surrounding sedimentary strata at right angles. This vertical sheet was so thick that it cooled slowly enough to develop horizontal columnar jointing in its central portion. Along the margins, the dikes are very fine-grained because they've been chilled against the colder sediments. Most of the sills and dikes in Ardnamurchan are basaltic in composition, but they're not always uniformly fine-grained. Now this is another vertical dike, and it's a rather interesting rock because it's jam-packed full of crystals. It's porphyritic. And some of the big feldspar phenocrysts in it are more than 5 centimeters across. These big phenocrysts probably grew in the magma before it was intruded to form the dike. Further along the coastline, there are other kinds of intrusions. Here, the shallow dipping sedimentary strata are also cut by numerous inclined sheets. They're neither sills nor dikes, but they are composed of the same basaltic magmas, and they also have chilled margins where they've cooled against the cold sediments. Here, these shallow level inclined sheets all dip in approximately the same direction, but they vary quite a lot in thickness. This one's less than 20 centimeters thick. And here's another one of these thin inclined sheets. It's concordant with the sedimentary layering. And here, a thin leaf peels off and snakes away down, progressively more discordant with the bedding. And the main sill itself, if you follow it along, begins to change. It curves over and becomes discordant with the bedding. So these shallow level intrusive sheets aren't always nice, straight, regular features. They bend, or they bifurcate, or they do both. Around the Ardnamurchan Peninsula, these small intrusions cut through the sedimentary strata, and it's possible to use the cross-cutting relationships to work out the relative ages of the igneous and sedimentary structures. Now this is rather a thick igneous sheet, and it's dipping that way at about 20 or 30 degrees, strongly discordant with the sediments, which are dipping the other way. And over here, there's another intrusion. A thin, sinuous dike cuts up through both the sediments and this inclined igneous sheet. We've got some very nice age relationships here. These sediments have got fossils in them. These are the remains of squid-like creatures called belemnites, and fossils like these tell us that the age of the sediments is Jurassic. And this igneous sheet cuts the sediments, so it must be younger than they are. And in fact, we know it's about 100 million years younger. And this dike must be younger than both of them because it cuts both the sediments and the inclined igneous sheet. About 100 million years ago, sedimentary strata were deposited with the remains of belemnites in them. They were tilted around 60 million years ago, and then they were intruded by inclined sheets of magma. A few million years later, the whole region was cut by vertical dikes. In parts of the coastline, there are so many inclined sheets that there are only thin screens of the older sediments between them. Here, they're all dipping in the same direction, in towards the center of the peninsula, and they do the same around the rest of Ardnamurchan. If you plot their outcrop patterns on a map of Ardnamurchan, you find that they form roughly concentric arcuate structures, all dipping towards the center of the peninsula. Beneath the surface, they dip towards a single focus. They form a cone. These inclined sheets are in fact usually called cone sheets. So far, we've only looked at small-scale minor intrusions. They cut the sediments that surround the much more massive structures occupying most of the peninsula. In the center of Ardnamurchan are well-exposed massive rocks, which are volumetrically enormous.
The surface is rather weathered, and if we look at the surface of a specimen, we can see a variety of different minerals. We can see this rusty, weathering olivine. We can see dark green pyroxene. We can see these very white areas of felspar. But not all gabbros look like that. This is a gabbro that I've collected from another part of Ardnamurchan. You can see that it's made up of similar proportions of those minerals. But it's obviously very much finer and darker in colour. But both of these rocks have got very similar mineral and chemical compositions, so they're clearly different varieties of gabbro. And the most common rocks that form the igneous centres of Ardnamurchan are all gabbros. That means they're relatively enriched in iron, calcium and magnesium, and they all have about 50% silica.
Because these gabbros have different textures, they weather and erode at different rates, producing a variety of landforms. The most coarse-grained gabbro has been the most resistant to erosion and now forms a large ring of mountains, 6 kilometers in diameter, in the center of Ardnamurchan. These ring-like features are so large that they can best be seen with the aid of aerial photographs. The ring of gabbro mountains is the most prominent feature, but it's possible to see several concentric structures in the middle. These circles mark the structures within and between the different gabbros, and together they mark the shape of a huge magma chamber, now solidified and later revealed by glacial erosion. Around the edge of this ring of gabbros are the truncated remnants of other circular structures. They mark the positions of older magma chambers. The Ardnamurchan igneous centre developed in several stages with a series of different magma chambers, 1, 2 and 3 in slightly different positions. So the focus of the igneous activity clearly shifted with time. These magma chambers were connected to volcanoes above Ardnamurchan. One explanation of how these magma chambers formed is that cylindrical blocks of the Earth's crust subsided, a bit like a pudding dropping out of an upturned bowl. Magma already present beneath the surface welled up to fill the gap above the subsiding block. Repeated subsidence introduced a series of magmas, one after the other, all rather similar in composition, but each cooling at a different rate. These steep-sided circular intrusions are called ring dikes. Later pulses of magma produced the cone sheets. They cut through the surrounding sedimentary strata and through the gabbros in the magma chambers, which by this time had solidified. The distribution of the gabbros and the patterns of the shallow-level minor intrusive sheets, especially the cone sheets, show us that the volcanic center of Ardnamurchan has got a definite structure, and there's clear evidence of repeated pulses or injections of magma from the mantle into the crust. Some magma erupted at the surface, some solidified in cracks and fissures to form the sills and the dikes and the cone sheets, and large volumes of it crystallized to form the massive gabbros of the ring dikes.